Suppose we're given the table about bank customers at a small bank. In this table, we have listed across the top, cashing check, no check. This is the events that someone went up to the teller window, they either cashed a check or they didn't cash a check. We also have the events that they made a deposit or they didn't make a deposit listed in this table. So for instance, if I look at that number 50 there, that means that they went up to the window, they cashed a check, and they also made a deposit. The number 30 means that they cashed a check and didn't make a deposit, so there are 30 people that did that. That they did not cash a check but made a deposit, there were 20 people who did that. That they didn't cash a check and that they made no deposit, there were 10 people that did that. And then we've also got the totals listed for the rows and the columns around the outside here. So with this information, we could use empirical probability and figure out what's the probability that someone would make a deposit. So that's going to be the number of people who made a deposit divided by the number of things in the sample space, 70 divided by 110. I could also figure out what's the probability that they did not cash a check, and that would be the number of people who did not cash a check divided by the number of people in the sample space. So the number of people who did not cash a check would be the 20 plus the 10 to give the total of 30 out of the total number of people, which is 110. So this is just using the tools that we've had from previous sections. What we're going to change here is suppose we want to know the probability of making a deposit given the fact that a check was cashed. So the way we would write that out is we'd write out P parentheses, make deposit, a vertical bar, and then cash check. So the way we would read that is the probability of making a deposit given that we cashed a check. So the vertical bar we read as given. To calculate that, it's pretty straightforward. We know the people cashed a check. There are 80 people that cashed a check, and of those 80, 50 of them made a deposit, so the probability here must be 50 over 80. Pretty straightforward. So essentially what we've noticed is we went from having a sample space that had 110 in it down to 80 because we know they cashed a check. Now, an alternate way to look at this is to take the exact same given that they cashed a check and the probability that they're going to make a deposit. The definition of conditional probability, which is what we're doing here, is that you do the probability of making a deposit intersected with cashing a check divided by the probability of cashing a check. Making a deposit and cashing a check, well, that's that 50. So the probability of doing that would be 50 out of 110. And then the probability of cashing a check would be the 80 out of 110. So 50 1/10ths divided by 80 1/10ths gives me 50 80ths. That's the exact same answer we got before, but now we're using the definition of conditional probability, whereas before we just kind of did it intuitively. Suppose now we want to know the probability of not cashing a check given that no deposit was made. Let me go ahead and use the definition. So that would be the probability that you did not cash a check intersected with that there was no deposit was made divided by the probability that no deposit was made. So no check, no deposit would be the 10 here out of 110. No deposit would be the 40 out of 110. 10 over 110 divided by 40 over 110 gives me 10 40ths, or 1/4, and now that should make sense because remember, no deposit, that was 40 people, and of those 40, we want the 10 who did not cash a check and did not make a deposit. So we can see the answer here intuitively, 10 40ths, or we can work from the definition of conditional probability. So that definition is that the conditional probability of an event E given an event F, written P of E given F, with the vertical bar being the given, is the probability of E intersected with F divided by the probability of F. And in that case, because P of F is in the denominator here, we can't allow that to be 0. So that's the definition, but we'll often use the definition. Sometimes we'll just work with that intuitive sense of what's going on. They're exactly the same thing. So if I take our definition, P of E intersected with F divided by P of F, and apply our definition of probability, which means the number of things in E intersected with F divided by the number of things in the sample space, P of F becomes the number of things in F divided by the number of things in the sample space. The number of things in the sample space cancel out, and we're left with N of E intersected with F divided by N of F. That's exactly what we were doing when we were counting the 10 and the 40. We were figuring out how many things were in the intersection and then how many things were in the F. They're exactly the same. In some situations, though, it may be easier to apply the probability definition versus the intuitive notion of counting things up. Suppose two coins are tossed and it is known that the faces match. Find the probability that both were tails. Intuitively, you would think the answer is 1/2, because if the faces match, that's 2 possibilities. Both were tails, that's 1, so 1 out of 2. But let's use the machinery that we've built up to this point to figure it out. Our events are E, both were tails, and F, the faces match. So here are those actual events. E is tails, tails. F is tails, tails, and heads, heads. And the sample space here is tails, tails, heads, heads, tails, heads, heads, tails. So applying our definition, we're looking for P of E given F. So that'll be the probability of E intersected F divided by the probability of F. And E intersected with F is just the event tails, tails. So the probability of that is 1/4. And the probability of F, there are 2 things out of 4, so that's 2/4. And when you divide 1/4 by 2/4, you get 1/2. So we get the exact same answer that we would intuitively think we would get. So suppose 2 cards are drawn from a standard deck. Find the probability that the second card is a heart, given that the first card is a heart. And here, I'm going to go ahead and use that intuitive notion. We want the probability that the second card is a heart, given that the first card is a heart. And remember, we've pulled 1 card out of the deck and found that it was a heart. So when I go to grab that second card, there's only 51 cards left. And because I've taken 1 of the 13 hearts out already, there are 12 hearts remaining. So the probability here, given that the first card is a heart, is 12/51. I don't need to go through using the definition of conditional probability. I can figure it out intuitively just by counting things up.